So we were talking about molecular orbital theory and bond orbital theory. So here, doing lithium, remember we have these orbitals, molecular orbitals fill up in order just like we did with electron configuration. So lithium has one 2s electron, 2s1. Don't worry about the 1s2s, because those will cancel each other. So you go to 2s1, two lithium atoms. So both electrons are going to go into sigma 2s molecular orbital. So the bond order is 2 minus 0 divided by 2 is 1. So Li2 is a stable compound. If we go up to beryllium, which has two 2s electrons, so it'd be a total of 4 electrons if we try to put both of them together. 2 of them go into the bonding molecular orbital, 2 of them into the anti-bonding. So it's 2 minus 2 divided by 2, which is 0. So bond order is 0. Be2 does not exist. So here we're looking at a picture of molecular orbitals. And instead of question mark, it should be P molecular orbitals. So remember, P is dumbbell shaped. And if you do P molecular orbital, you have in the center there the bonding orbital and those two little lobes on the outside that look like ears attached to it. Those are the anti-bonding P orbitals. So there's the molecular orbital. And there's more bonding and anti-bonding orbitals for pi orbitals. So if you're looking at compounds like oxygen and fluorine, we have the sigma 2s followed by the sigma star 2s, the antibonding. The 2px, so that's the p or sigma 2px along the x-axis. Then the pi 2py 2pz, then 2py 2pz antibonding, and the sigma 2px antibonding. If you're looking at compounds like lithium, boron, carbon, and nitrogen, it's changed a little bit. You see the pi 2py and the pi 2pz come below the sigma 2px rather than above it. That you fill those in a different order. Best thing to do is look at the table in your book. So again, we fill up the lower energy levels first. Each orbital, 2 electrons, opposite spins. And Hund's rules apply, which means if you've got 3 orbitals, same energy level, they don't pair until you have to pair them. So if we look at Li2, well, we did Li2. B2, well, boron has how many valence electrons? 3. So if I'm going to put 2 borons together, I have a total of 6 electrons, 3 from each atom. So if I look at boron, start from the bottom, 1, 2, 3, 4, 5, 6. So I have, what is its bond order? I have 4 in bonding orbitals, 2 in an anti-bonding orbital, so it's 4 minus 2 divided by 2, so its bond order is 1. Everybody see that? I have 2 in the sigma 2s, and 2 in the pi 2py 2pz, so that's 4 in bonding orbitals, and then 2 in the sigma star 2s. If you look there, the 2 that are in the p2, py, and pi 2pz are unpaired. So that means B2 is paramagnetic. So if I go to C2, carbon has 4 valence electrons, the 2 carbons together, that's 8 valence electrons. It fills in like that. So now I have 2, 4, 6 in bonding orbitals minus 2 in the anti-bonding orbitals, which is 4 divided by 2. Its bond order is 2. So it's more stable. None of them are unpaired. They're all paired, so C2 is diamagnetic. Go to N2. Okay, nitrogen has 5. So if I put two ends together, I have 10 electrons to put in, and that's how they go in. So I have 2, 4, 6, 8 in bonding orbitals minus 2 in antibonding, which is 6 divided by 2. So it's a bond order of 3, so that's even more stable. None of them are unpaired, so N2 is diamagnetic. Come to the other side, and you can see it's a little bit different table. The pi and the sigma swap places. If I go to oxygen, 16, 12 rather, oxygen 6 valence electrons, 2, 4, 6, 8, 10, 12. Well, if we look at that, we got 2, 4, 6, 8 in bonding, minus 4 in anti-bonding. 4 divided by 2, so its bond order is 2, and there's 2 unpaired, so oxygen's paramagnetic. Fluorine, 14 electrons. This fluorine has 7, so I have 2 is 14. Bond order is 1. None of them are unpaired, so it's diamagnetic. And if we go to neon, let's say we're going to make Ne2, so we're doing with 16 electrons. Neon's column 8. If you figure out the bond order, it's 0. 8 minus 8. So Ne2 does not exist. So if we're talking about heteronuclear atoms, the ones we had here are all diatomic. 2 different atoms, such as NO. The atomic orbitals of the more electronegative atom are lower in energy than the corresponding atomic orbitals of the less electric. So the lower energy atomic orbitals contributes more to the bonding molecular orbitals, and the higher energy atomic orbitals contribute more to the anti-bonding molecular orbitals. So the bonding it more closely resembles the atomic orbital of the more electronegative atom, and the anti-bonding less electronegative atom. So what that results is the electron density is greater in the vicinity of the more electronegative atom, which makes sense. The more electronegative atom wants the electrons more. So here we're looking at nitrogen and oxygen, I assume. So how many valence electrons? Oxygen has 6, nitrogen has 5, so total number of electrons we're dealing with is 11. 2, 4, 6, 8, 10, 11. Let's look at the bond order. 2 in the sigma 2s, 2 and 2px, that's 4. And in the pi, 6, 8. 8 in the bonding. The anti-bonding has 3. So 8 minus 3 is 5. 5 divided by 2 is 2.5. So it has a bond order of 2.5. That's perfectly all right. Is it paramagnetic or diamagnetic? Quick. Why? Yeah, it has an unpaired electron, so it's paramagnetic. The superoxide ion, O2 minus, so it had implicated in a number of degenerative conditions, including aging, okay, and Alzheimer's disease. So let's see if it's paramagnetic or diamagnetic, and then calculate its bond order. So how many electrons am I dealing with in O2 minus? 13. So oxygen has 6. There's 2 of those plus 1 electron to make it negative. So I'm going to go, there's the setup. Put in the 13 electrons. What's its bond order? Bonding minus antibonding divided by 2. I come up with how many bonding electrons? 8. How many antibonding? 5. Okay, higher math. 8 minus 5 divided by 2. 1.5, yeah. Is it diamagnetic or paramagnetic? Quick. Para. Yeah, we have a lone electron, so it's paramagnetic. It says paramagnetic and its bond order is 1.5. Remember earlier on we talked about, odd number of electrons? We called those radicals. Well, there it is, the superoxide is a radical. Questions? Oh, how come they got a 6 minus 3? See the sigma 2s and the sigma 2s prime? They didn't count those because they cancel out. They took a shortcut. I wish they would have done that, but it comes out 1.5 in either case. So let's describe molecules with delocalized bonding. So the Lewis theory, what is its strength? We can make qualitative predictions about bond strengths and bond lengths. And Lewis structures are easy to draw, right? Because it says right there, they're easy to draw. So they must be easy to draw. Okay. And chemists widely use them because they're easy to draw. Weakness is they're two-dimensional, and we live in a three-dimensional world. And it fails to account the differences in bonds in compounds such as H2F2 and HF. And it also fails to explain why bonds form. So we're just, the valence shell electron pair repulsion model of VSEPR, what is that good for? If we can predict the shapes. We did a lot of that predicting the shapes of the molecules and polyatomic ions. Oh, but it's based on Lewis structures, so it has the same of the weaknesses. It doesn't tell us why bonds form. The valence bond theory describes how covalent bonds are formed by overlapping atomic orbitals, and it lowers the potential energy. So now we know why bonds form, but it fails to explain the bonding in many molecules like BeCl2, BF3, and CH4. Because remember, if you look at carbon, there's only 2 unpaired electrons, yet carbon forms 4 bonds. So it really kind of fell apart there. So then they went on to hybridization of atomic orbitals. So it's an extension of the valence bond theory. And by doing the hybridization, we can explain why BeCl2 exists, CH4 exists, and so forth. But it fails to predict certain properties, like if a compound is paramagnetic or diamagnetic. Which then came to the molecular orbital theory. That helped us predict whether it's paramagnetic and diamagnetic. The weakness is that pictures of molecular orbitals can be very complex. We've only looked at simple ones. There's people who spend their whole careers doing molecular orbital theory calculations on more complex molecules. So they go to things like highest occupied molecular orbital, lowest unoccupied molecular orbital. They spend hours in front of computers running simulations, all to predict whether a compound's stable, whether the bond is stable, which way it's going to go. So it gets a lot more complex than what we looked at. So here, if we look at benzene, benzene, 6 carbons, and we'll draw like a hexagon, and there's H, or H here, each one. Alternating, well, we draw it, alternating double bonds. So what is the molecular geometry around each carbon? What's the hybridization around each carbon? These are carbons. How many things are on each carbon? 3. So what's its hybridization? What's its hybridization? Quick. sp2. Remember, it's got to add up to 3. So it's sp2. That tells me its molecular geometry is, no, it's not tetrahedral. 3 things. Trigonal planar. So you can see up there on the left, the sigma bonds. Those are just the sigma bonds. So here we do the promotion, right? We take the one of the 2 s electrons and moves it to the empty 2p orbital. But we're only going to do sp2, so we're going to take these 2 and the 2 p's and the s and put them together to give us 3 sp2 orbitals. So now we have the sigma configuration. What do we have left over? We have an electron in the p orbital. Remember, the electrons in the p orbital form what kind of bonds? They're not sigma. Pi. Apple, cherry, the peach, it doesn't matter. Form pi bonds, okay? So remember, the pi bonds are perpendicular to the sigma bonds. They're the dumbbell shape that overlap. Well, if you do that with benzene, you can see how they end up overlapping. They go all the way around the molecule. So those electrons are delocalized all around the molecule. So compounds like benzene that are called aromatics have completely different properties with just compounds with double bonds. Compounds with double bonds, just like say if I did this, completely different properties. The electrons can be delocalized here and here. But once I do this, now they're delocalized over the whole thing. Much more stable. So their chemistry changes drastically. Way back when we were doing Vesper diagrams, we did the carbonate anion. I remember we had 3 resonance structures. That's how we showed it. So if we're going to use combinations of valence bond theory and the hybridization theory, let's see if I can draw this here. We have CO, I'm not going to draw the unpaired electrons, O. What is the hybridization around the carbon? Give me the actual hybridization. What? sp2. Around the carbon, right? Well, let me put. So we know the carbon is sp2. hybridized. So the sp2 hybrid orbital on the carbon overlaps with a singly occupied p orbital on an oxygen atom. So we have 3 sigma bonds. I know it says S, but it's sigma. So I know I can say, okay, we have this. Here's a sigma bond to an oxygen, a sigma bond. Here's a sigma bond to an oxygen. And here's a sigma bond to an oxygen. 120 degrees apart, critical pointer. Each oxygen atom has an additional singly occupied p orbital perpendicular to the one from the sigma bond. And we have a leftover p electron for the carbon, right? So we can draw, well, they don't draw it that way. What happens? We don't have. So even though it looks like that, because you see the double bond is actually not on any specific oxygen atom, it goes back and forth. Since this oxygen has a P, this oxygen atom has a P, and this oxygen atom has a P. Carbon atom also has a P, but I can't draw it right, but the way it overlaps, it can be on any of the oxygens. So it's delocalized over all 3 oxygens. So it's not like you have one carbon-oxygen double bond. If you measure them, they're all the same length. And then it flips back and forth. So it's delocalized over all 3 of the oxygen atoms. You understand? Kind of?
So if you use those drawings, correct?
Yeah, technically they're correct, I mean, in terms of fluid structures. But what that stands for, because the resonance means that it's delocalized over all those oxygens. Just like if I drew, when I drew benzene, I drew it this way, the resonance structure would be, just flip them around, those are equivalent. Sometimes you get, it's represented in some books this way, where the circle means those pi electrons go all the way around the ring. So if you ever see that, that's what it means. So the double bond, the pi electrons in carbonate aren't on one oxygen atom, they're delocalized over all 3 of them. So that's why everything looks the same. And that is the